So we're going to try to polarize a material. So let's immediately, not now. I'm not enjoying you. I can show this thing. There you go. Let's polarize a material. We're going to start with the scalar potential phi. So phi of a dipole. Oops, phi of a dipole is simply phi is the dipole moment d dotted with r vector over r cubed. Of course, we can write this as d vector r hat over r squared. And then, of course, we want to make sure that we note that the potential of that dipole goes with 1 over the distance squared, as opposed to the potential of a monopole, which goes like 1 over distance. Okay, so it goes faster because, of course, dipoles, as you move away from them, you don't only have a reduced potential because of the 1 over r, they also start to appear closer together. So they start to cancel each other out. So what we now want to do is when we want to say, well, let's say we have some kind of a material, and in this material, we have all sorts of dipoles. So there's a little d here, and there's a little d there. And then, so this would be d1, d2, d3, etc. And we want to find the potential due to all of those dipole moments. So we just need to add the contribution of all of them. So that would be phi of r. So I'm going to write this explicitly with the r there. So this would be enumerating the positions and the momentum, position and the dipole moment of the individual dipoles, and then divided by, okay, r minus ri. And this is, of course, to the power 3 because that thing in the numerator is a just an actual position vector difference. It's not a unit vector, so we need the r cubed version. So the ri's are basically pointing, this is r1, and that's r2, and then that's r3. And of course, those vectors are supposed to point to the center of the dipole moment, but that's okay. Okay, now we can change this to an integral formation where we say use a dipole moment density. So this is the dipole moment density, such that when we have an infinitesimal dipole moment, we can relate that to the density by simply taking p and then integrating that over the volume. So then what we can do is we can write our sum in an integral instead. So then this becomes an integral. Now the dipole moment density goes here, and then we need to now explicitly say what the positions are, where they are as an argument to that vector field P that describes what the polarization, or sorry, what the dipole moment density is at that location. And then this part stays the same. So there's an R prime, but that Ri became an R prime, right? You see that? And then the numerator, we have the same thing. We replace R prime. And then the thing we're integrating over is the primed coordinate. So that's the d3, or so the d cubed 3x. Okay. Now, we have used the following identity a couple of times. Um, this this thing here, you can actually write as the gradient of 1 over the as the gradient of 1 over the distance. So we're going to rewrite this. We still have the p that remains unchanged. And then we're dotting that with the gradient. And it's the gradient with respect to the primed coordinate. So that's why the gradient has that prime on it. And then it's the gradient of a scalar quantity, which is simply 1 over r minus r prime. So it's the magnitude of that difference in positions, and then that inverse, which is a scalar thing. And if you take that gradient, you get the same function. So this thing in the blue box, these things are the same. And then, of course, we still need to integrate over the volume. Okay, now now we're going to integrate by parts. So this is integrate by part. That means that we pull out, and I'm going to write explicitly now a volume here. We're going to pull out that gradient in front of the whole thing. And then that is operating on P prime over, and this is R minus R prime. And then that's still an integral over the primed coordinate minus, and then this is still part of that same volume integral, but now here we have the term we need to subtract because we moved the Nabla operator in front of that P and that 1 over R. So we have to subtract this part that would arrive from the product rule. And then, so this is still an integral. And then this is 1 over, let's see, that's R vector, R prime. And then that's a d3x prime still. Okay, now we can change this this first part into because it's the divergence, right? So we can use that theorem that can change the divergence into a surface integral. So now we have a p r prime. Oh, that's a p vector dotted with the normal, and then that's d2s prime divided by, well, it's still that same thing. Now, this is the, and then this thing stays the same. And this is the potential, right? So this is the potential phi of r. Now, compare this to the general solution for phi of r from an arbitrary charge distribution. We would have the integral of rho r prime over d3x prime divided by that r minus r prime. Okay. If you look at this expression, hopefully you see that there are some things here that look the same. The let's see, where did my thing go? This, compare that to this, looks like a charge distribution. Looks like rho, right? So that divergence of the polarization, or the divergence of that dimension, sorry, the dipole density looks like a density. So the things in green, they look alike, right? Because we have a potential that looks like it's a volume integral of something over the distance, and that something over the distance has also an extra minus sign there. So that's okay. So what we need to do is we need to now write this as as a uh, as a new kind of a charge density. So we're going to call this thing the polarization density. So let's call the divergence of P with a minus sign the rho of the polarization density. And then if you see that same P shows up there, but the P is dotted with a normal, that we're going to call a sigma polarization. So it's also using that same P, but it's now dotted with the normal. Okay, so we have we have phi now, but with those new definitions. So phi of r is simply that that integral over the that's annoying. That integral over the surface where we have the sigma polarization as a function of position, and then divided by r minus r prime. And then this is a surface integral. So that's a d2 d2s prime. And then we add the integral of that polarization density. So that's rho polarization, r vector. And then divide that by the distance as well. And then that's a d3x prime. And then we have defined those two. There's a d3x. d3x prime. And we've defined that sigma and that rho using only that polarization density. So rho polarization is minus the divergence of that polarization density, which is the dipole moment density, right? But now you see what it is. And this is just whatever that P is once you dot it with the normal at a surface. And we will solve an actual boundary value problem, and you'll see this thing actually play out. Okay, now we have in general, so we can have the potential in general of some kind of charge configuration in space be a function of both rhos that are present as well as materials that might have a polarization in them. So we should say that the total charge that can lead to a scalar potential should be not only that rho polarization, but also the rho that we already had. So, so the rho, we're going to define that as the rho of free charge carriers and the rho of this polarization. And then Gauss's law should say that the divergence of that should be 4 pi times, well, now I have to take rho free plus the rho polarization. But the rho polarization is actually minus the divergence of P. Okay, so that means that we can, oh, there's a 4 pi here. 4 pi divergence of P, which means that we have a divergence here, we have a divergence there. We can move this whole thing over to the left and then call this thing E, and now it becomes positive, plus 4 pi P. And then on the right-hand side, we simply have 4 pi rho free. And now this thing we call D. It's the displacement field. Okay. And then we can just call this the new Maxwell's first equation. So Maxwell 1 for polarizable materials. Is just 4 pi rho free. Okay. Okay. Now for a simple dielectric material, so nothing nonlinear, we can usually assume that the polarization is going to be proportional to the electric field. And in fact, it is proportional with a simple scalar quantity chi, which is the susceptibility, E, so that we can write D is simply E plus 4 pi P equals E plus 4 pi chi, and then that's E. Or in other words, it's E times 1 plus 4 pi E. Okay, so we can now call this epsilon the relative dielectric constant, such that D is epsilon E in simple materials. And then so capacitances get rescaled with that same E. Okay. Let's do an example. Good, just that. And it's nice that it's a finer thing. So let's use an example. Actually, hang on, I'm moving too fast. Okay, so I should summarize this. So we have the so we have this new Maxwell's equation where that P field, so there's a polarization here. That's the P field. And where that P field meets the normal is where you get the sigma polarization. And then this in the material is the rho polarization. So that's how you should think about it. And they're basically that P field, when it terminates at the normal, that's where it constitutes sigma, so surface charge density. And then the boundary condition is as follows. So boundary conditions go like this. So let's say you have some kind of a material, then you have, Gauss's law. There's a D1 here, and then there's a D2 there. This is material number 1, and this material number 2. That boundary condition you can now write using Maxwell's equations as D2 times the surface area, so that's the surface area that sits here, D2 times the surface area minus D1 times the surface area is 4 pi Q free, where Q is just the Q that sits here, Q free. And that's how you do boundary value problems. Okay, now let's do this example. So example, a capacitor. A capacitor. And then, okay, let's see, control this line. There you go. So first we start with a capacitor like this. It's it's a parallel plate capacitor. We have a 2 leads. One side is positively charged. Da-da, da-da, da-da. The other side is negatively charged. So that means that inside here there's an electric field. And here on the edge, of course, we can consider fringe effects if you want. But I'm gonna let you think about the following. What this thing looks like when you add a dielectric material. So we're gonna have the same capacitor, but now in this capacitor we're gonna have a dielectric material. So that's gonna sit here. So just a slab. Let's say it's a piece of glass or something. So this is a dielectric material. And so I want you to draw, let's see, let's see, sigma polarization. E, E1 and E2. Let's call this 2, 2, and then call this 1. Yeah, so let's see, so that E2 would be in green. Yeah, there you go. E2 will be green. And then let me see, sigma polarization E and E1. Yes, I want to let you think about this for a minute. All right, let's go over this. So the first thing we do is we use the boundary condition, and the boundary condition is that the difference between the two displacement fields across that boundary must be equal to 4 pi sigma free, but in a piece of glass, there's no free charge carriers. We'll do a conducting piece later. But if that sigma free is 0, that means that D2 is D1. Okay, that's good. So in region 1, there is no polarization because it's vacuum. So in region 1, D1 is simply E1. So those are the blue fields, D is E. And then because of the boundary condition, that D1 is equal to D2, and the D2 can be written as that E2 plus 4 pi times the polarization density. And that polarization field is in the same direction as E, because that's usually what the polarization does, which means that E2 is actually E1 minus 4 pi times P, which means that E2 is smaller than E1. So what does that mean? Well, we need to draw E further apart. Okay, so this is E2. And then P is in the same direction, right? So let's call this P. P is in the same direction. Okay. Now, that P, when it meets the surface, there's a normal here. So that's the normal. Normal. So when P hits the surface on the top, the P and N are pointing in the same direction. So the polarization charge density is positive. So let's say, so here, N dot P is greater than 0. So sigma polarization is also greater than 0. And here it's the opposite, because the normal is down, but it's still the same P field. So here it's negative. So therefore you get this induced polarization on the surface that just sits there, and it's just negative, 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 and it's positive, positive, positive. Da, 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 da. Okay, now finally, you know that delta V is simply negative EDL. So in a capacitor, we now know that if you insert that slab of a dielectric, the electric field there is going to be smaller. So if the electric field becomes smaller, the potential difference becomes smaller. Okay. What does that mean? Well, it means that C is Q over V becomes bigger by inserting the dielectric. And that's, of course, as we know, because we know that if you make a capacitor, you usually want to put a dielectric in between, not only to separate them, so keep them physically separate, but also to increase the capacitance. So you get the same capacitance for a more compact packaging. Okay. That's with a dielectric. Now, if you put a metal in, it's a different story. So then in that case, come on. So with a metal, so now let's say this material is a metal. So this is a metal. The boundary condition is still the same. So you still have D2 minus D1. It's 4 pi sigma free. But your E field is 0 here, right? So E field here is 0. Okay. So if that E field is 0, then that means that you need to have a polarization that corrects for that, right? So if D1, what do we call this? Okay, this is 1, this is 2, that's 1. Okay, so D1 is E1, and then D2 is it's it's E2 minus that. So you get an induced charge, and it's like positive here. So this is negative. and it's positive. Yeah. All right. Now, the magnetic materials deserves um, its own new thing. Hey, where's my? There we go. Okay, magnetic materials. Materials. Um, so we have a current density in general. Um, it's going to be a J free plus a J convection. So J convection is it's a little bit strange. It's basically it's charge carriers uh, stationary in a medium that moves. Um, we will just assume that we don't have to worry about them, but rest assured that they're just charge carriers. They move in a medium, but it becomes a little trickier because now you need to treat that whole thing completely self-consistently. Okay, now for the free um, charge density, there should be a continuity equation. So continuity equation that says that J free plus the derivative of the charge density free is 0. So now if we consider this capacitor, so consider this capacitor again. So if there is if we turn on the power, there will be a buildup of rho and sigma. There will be a buildup of rho. Oops, that's not a rho, that's a p of rho and sigma and p. And there should be also a continuity equation for that. So we find that as follows. So we say that the ddt of the rho polarization should be negative the del t of the divergence of p. That's by definition, of course. So therefore, we can write del t for the rho polarization plus the divergence, and we're swapping the derivative del p del t is 0. So that's a continuity equation. Looks just the same. So it's a continuity equation for the polarization. Polarization. And we can generalize this, and we call that dp dt. We can just simply call that the current. So this thing, the J polarization. So polarization current. And then it is fully in this form of the J polarization of the continuity equation. Okay, now before we were saying, well, we have free sources that we call sources of the type number one. We have convection sources, and we ignore those. That's number two. And these are polarization currents. These are your sources of type 3. Okay. Now, so I'm going to now do magnetization, but I'm going to write next to it the corresponding steps from when we were doing polarization, because it's going to be easier to recognize it. So magnetization. So when we're doing magnetization, we're always using the vector potential instead of the scalar potential, of course. And then it has that, oh, that's an actual vector, has that same structure. And then with polarization, the workhorse is this dipole phi, which is d r over r cubed. So we can write phi as an integral over a polarization density, r minus r prime, over cubed, that's a d3x prime. And we could do a similar thing here. It just looks a little bit more dicey because, of course, now we have a cross product here, but the logic is the same. When we do this, that's r vector, r primed, that's a cubed, d3x prime. And now we're doing the same thing with that divergence trick. So we just say this is just crossing the gradient, but it's the gradient of the 1 over r minus r prime. And this is still d3x prime. And we did the same thing here. We said this is the integral of p, the gradient of, I'm going to just use shorthand here, okay, d3x prime. And then we did integration by parts here. So we got a surface integral of a p n d2s prime over r minus, and then we had the divergence of p over r, and then that's a d3x prime. So now we're doing the same thing here. We're using the same Feynman trick to do integration by parts. There's this trick where you split up the curl in a curl acting on E and a curl acting on B. That's an easy way to do this integration by parts. And then you get the magnetization density. So that's a D surface. Okay, that's R minus R prime. And then that's already integrated. Okay, that's now integrated over the volume. We have this thing over R prime d3x prime. And now this thing is surface magnetization current. Current. It's called K mag, and it's C M crossed with N. And this is the magnetization current. So J mag, which also we put into C, so it will work nicely for our Maxwell's equations. So now we have Ampere Maxwell. So changing Ampere Maxwell. So we have a curl of B minus 1 over C del TE is 4 pi over C J free. Okay, plus, okay, there's a del P del T because that's the polarization current. And then plus this magnetization current, right? So we need to consider all of them currents. That's J mag, that's polarization mag, okay? And now we can rewrite this as follows. Okay, we can write this B. Now the curl of this M is going to go here. So that becomes 4 pi M. And then that C, now you see why the C is there, because this C and this C, they cancel. And then we have something that neatly folds into that curl. And then we have a 1 over C, and then we have a del T. And now we still have the electric field here. But now we're going to take this guy there. So that goes here. So 4 pi P is 4 pi over C J free. Okay, now this one we had already defined. That's D. And this one is H. So that's the modified Ampere Maxwell current. And then the boundary condition problems are very similar to before. So let's say you have a little Amperian loop here, and you do you have a boundary between a problem medium 1 and a medium 2. So let's say the B1T is B2T is applied, and then we just get H2 minus H1 with the normal is 4 pi over C K free. And the most simple magnetic material, you can just set B is mu H. Most simple magnetic material. All right.